All right, welcome to another week of the Chem 1211 lab here in North Georgia. This week we're going to be taking a look at the emission spectrum of atomic hydrogen. It's going to be a little bit different lab because there's not going to really be any experiment we're going to specifically be doing. Instead, we're really going to be looking at just kind of data and doing calculations with data to try and help us better understand atomic structure and how atoms can just generally behave and interact, particularly with light. And so a little bit of background kind of on this. We're actually going to start by talking about light first. And then after we've talked a little bit about it, how we can kind of help relate this to things about the atom. And so light, when we talk about it, it's a form of electromagnetic radiation that we can see with just the naked eye. And in particular, when we're talking about electromagnetic radiation, there's a lot of different technical definitions we can try to be particular about. But I think the easiest way to usually think about this is just to view it as a form of energy that typically is associated as having a wave-like character. So it has a bunch of wave-like characteristics or properties that we're able to talk about. And so when we talk about light, since it has these wave-like properties or wave-like characteristics, we'll often be talking about its wavelength or its frequency. And we can talk about its amplitude, but as we kind of start talking about it a little more in depth here, you're going to see the amplitude is going to be a little bit less important. Just to kind of remind people of like what wavelength and frequency really are. If you are looking at a wave, so something looks kind of almost like a sine wave from like a mathematics course, your wavelength is the distance between peaks in that wave. Your frequency is a little bit different. It's basically if you pick a particular point in time, if this wave is moving, it's how many peaks are actually passing a particular point over some time interval. And it's usually going to have units then of like inverse seconds or hertz that you'll typically see for those units. And the amplitude would simply be the height of the wave, but in our case, like I said, the amplitude is not going to be all that important. And so really we're going to be focusing mostly on wavelength and frequency because those are the things that are actually going to be related to things like energy that then kind of translate to kind of behavior and how light interacts with atoms. One neat thing about wavelength here as we're looking at it, when we talk about light and particularly colors of light, different colors have different wavelengths. And so if you know the wavelength of light, you can actually kind of basically look at that as far as what color you would be looking at by knowing that wavelength. And so that's kind of a neat thing that you can do when you get to know the electromagnetic spectrum a little better. And so that's something we'll take a look at here briefly. The electromagnetic spectrum, what this is, it's really just kind of a collection of different types of electromagnetic radiation. Light is just one type. You've probably heard of things like ultraviolet, infrared, like microwaves, radio waves, gamma rays, X-rays. You've probably heard almost all of these at some point in your life, or actually even are probably familiar with at least a few of these. And really what this is just showing is what is the relative wavelengths and frequencies for some of these different types of electromagnetic radiation. And this little tiny narrow band here in the middle, this is what we can actually see with our naked eye, and this is what we refer to as light typically. And we see that the wavelength range here is only between about 380 nanometers to about 780. You'll see that maybe vary a little bit kind of on the ends, like some people say 400 to 800, things like that as far as what we consider our visible spectrum, things that our eye is actually capable of seeing. And you notice here as the wavelengths change, so do the colors that we see. And so like I said, that's something that is common here when we're talking about visible light. Now, one thing to note on this plot here quick before we move on, when we're looking at comparing wavelengths to frequencies, we see that wavelengths seem to be a lot smaller in value, and as our wavelength gets bigger, then our frequency actually was decreasing at the same time. So they're kind of oppositely related. And also number-wise, like our frequencies here do appear to be much, much larger, and that is pretty typical when we're looking at these values. Now, relating all those things together, like wavelength and frequency, and then also tying those things into energy. For the wavelength and frequency in particular, we can relate these two things with an equation, and so that's what we see here. The speed of light is going to, which is this constant c here, is going to be equal to, this is the Greek letter lambda, and that's what's going to represent wavelength for pretty much everything we see in this material, like this chapter that you're seeing in lecture. And then this is the Greek letter nu. It kind of looks like an italic V. That's what represents our frequency. Now, one thing to be kind of aware of here, this constant, 3.0 to the times 10 to the 8th, that's a kind of a rough approximation. If you want to be a little more particular with like more significant digits, I think the lab gives you a better value. It's like 2.998 times 10 to the 8th meters per second. But notice unit-wise, it is meters per second, which means the wavelength you put in does have to be in meters. That is important because we often talk about wavelengths in nanometers, and so that does mean there's going to be a lot of converting back and forth a lot of times. Frequency, like I mentioned earlier, unit-wise typically going to be hertz, which is the same thing as inverse seconds. So you're going to keep that in mind, again, unit-wise. Now, if we want to relate either of these things to energy, it's a little bit easier to do it for frequency. This is kind of the starting equation we often show for energy. Energy is equal to Planck's constant, that's what this h is, times the frequency of a photon. And one thing I do want to point out, this energy here in this equation, this is the energy of a single photon of light. So light, even though it has kind of these wave-like properties, as you talk about it more in lecture, you'll see that it also has particle-like behavior, which is one of the things that makes light very unique, but also kind of useful because it kind of relates to how we think of now electrons and kind of look at their behavior. And in this case, when we're talking about a single photon of light, we can use this equation to figure out the energy of that photon if we simply know the frequency of that particular photon of light. Or likewise, if we know the energy, we can find the frequency, since h is just a constant value. It's Planck's constant, 6.626 times 10 to the minus 34th joules seconds. Now, one of the options that you have here, if you don't know the frequency, but say you know the wavelength instead, well, frequency is just going to be equal to c over lambda, and you can just take that in down here, and you can have energy as hc over lambda as another way to calculate the energy also. It's pretty commonly used. All right, now, relating all this eventually back to the atom. Before we kind of tie light into everything here and talk about something called spectroscopy, we're going to take a look at just kind of our generic models of the atoms. And really, most of what we talk about for this lab relates to the Bohr model of the atom in particular. And so the Bohr model, somewhat related to the Rutherford model of the atom, which basically have a positively charged nucleus. And the Bohr model in particular, what it added, on top of this, the existence of this positively charged nucleus that Rutherford had proposed, is that now we have electrons going around that nucleus in circular orbits. And this model works really nicely because it did actually help to explain what we call this atomic line spectrum for hydrogen. Unfortunately, we're going to see here in a second, it only really works well for hydrogen, and then not a whole lot else past that. But the way we can explain what's going on is that as a particular atom is hit with light, like basically you're hitting an atom with energy is kind of how I think about it, if you're hitting it with light or a photon of light, what can happen is that photon, let's say there's an electron in this innermost circular orbit. That electron can actually basically take that energy and move to a farther out orbit where it's farther from the positive charge, or it's in a higher energy state, basically. We'll call that process excitation. We'll sometimes call that an excited state of the atom, because that electron's at a higher energy than what it really wants to be. It'd rather be close to the nucleus in this inner orbit, but by adding some energy, we knocked it to an outer one. Sorry. And then what happens is over time, eventually it's going to come back to that inner orbit through a process called relaxation. And that's when your atom is actually going to kind of give off light back. So it accepted, kind of absorbed a photon of light in order for the electron to move to an outer orbit. And then when the electron relaxes back to that inner orbit, it gives off a photon of light. An atomic line spectroscopy, this idea of an atomic line spectrum, that's the light that's going to be given off by the atoms kind of through that process. So atoms do have, like I said, have this ability to absorb light. Again, we call this kind of process excitation, where we basically have an electron that goes to a farther out energy orbital than where it's starting. And in particular, when we're kind of going through this, what we're going to look at for kind of this week's experiment is what happens when that electron eventually comes back down. It's going to return to an inner more orbit, so it's undergoing what we call relaxation, but it's not always going to go all the way straight to the innermost orbit. Sometimes it goes to just one that's a lesser energy than where it's at, and then we'll take another step maybe after that to get to the innermost one that's available. And so in the case of hydrogen, this is really one of the big things we'll be looking at, is kind of which energy levels are those electrons moving between to generate the lines that we see in these spectra. And to give kind of a visual image of what these spectra actually look like, here's an example. This is for hydrogen, for what we see in the visible spectrum. It's mostly black because what happens is those energy transitions are a very finite specific energy value, which are then going to correspond to one specific wavelength of light. So most of our kind of visible range here is black, with the exception of the few colors that we do see that represent the photons that are being emitted back by that particular atom. And we see that just because an atom has more electrons or is a larger atom doesn't mean it's going to have more lines in the visible spectrum in particular. For instance, sodium has one really intense line kind of in the yellow region. Hydrogen itself has 4 lines. If we look at helium, helium I think has 10 in the visible spectrum or more, or even depending on kind of where you cut off the visible range, maybe up to 13. And so big variation between atoms, but it also lets us identify atoms based on their line spectroscopy is something that's kind of useful that does come out of this. Now, in terms of equations and calculations and things that we'll talk about, the main equation that we'll be looking at, particularly when we're talking about atomic line spectroscopy, and so like trying to figure out like, what's the actual wavelengths here, they correspond to the energy level transitions from that Bohr model of the atom, which if I back up to kind of this model of our atom, if we label our innermost orbit n minus 1, or sorry, n equals 1, and then the second one would be n equals 2, and then n equals 3, and so on, we do have an equation that based on the energy transition between which energy levels the electron is moving, what the wavelength is going to be for that photon of light that's either being absorbed or emitted. That's what we can use this equation for in particular. Now, for this equation, the way it's currently set up, if we're talking about emission in particular, so basically looking at an atomic line spectrum and trying to figure out what's the wavelength of those photons coming out of that atomic line spectrum, what the M and the N are going to represent. The M is the energy level that basically we're relaxing to, so it's where we end up. It's the lower number of those energy levels. So let's say we're at an outer energy level, energy, say our N is 4. If we're relaxing down to, say, N equals 2, the M would be 2, and the N would be 4 in that case. It's kind of where we start. And then we have the lambda is going to be the wavelength of the photon emitted during that process. And R here is a constant. It's basically just what we call the RYDBERG constant for this equation. We see here its value along with its units. And in particular, you might see a different version of this equation. I'm sorry, of this constant. It might be 1.097 times 10 to the minus second. And instead of inverse meters, it might be inverse nanometers for the unit. So do pay attention to the units on this constant, because those will be the units of the wavelength you're effectively going to get out. If we have inverse meters here, the wavelength itself will be meters. If we have inverse nanometers over here, we'll get nanometers on that wavelength when we do the calculation. And for everything we're going to be looking at in this week's lab, and this is kind of an extra piece of information that we use to kind of help do a lot of our calculations, the M value right here for everything we look at for hydrogen is going to be 2. Because it turns out the only transitions for hydrogen that we can see in the visible spectrum are always going to end at that second energy level. So this M value right here is going to be 2, and the N value is going to have to be something larger than that. It's coming from a higher energy orbit down to that N equals 2 level. All right, now the lab this week then, I think that's hopefully enough of the background information to kind of get started with things. And I think as you do things more in the lab, hopefully it'll be easier to kind of get used to those equations and use them. But the big thing is really just pay attention to units on those equations are probably the biggest thing to look out for, particularly on things like the pre-lab quiz. In the lab, though, when you get there, what we'll be doing after our pre-lab quiz this week is we're actually providing you with most of the recorded kind of experimental data. And you can see this actually already on CSE Pub if you go and look. And what we're going to be doing is we're going to be taking a look at both a hydrogen line spectrum and a helium line spectrum. And we're going to use the helium line spectrum to generate what we call a calibration curve. And I'll explain kind of what that is here in just a moment. But once we have a helium line calibration curve, what we're going to be able to do is use that calibration curve to figure out what are all the actual wavelengths for the hydrogen line spectrum. We can actually figure out what are each of those individual wavelengths that we see in its spectrum. If we know the wavelengths of all the ones in the helium spectrum, and then again, we're going to do that using this calibration curve. And then once we know the wavelengths for our hydrogen line spectrum, then we can actually identify the energy transitions that are happening to produce those hydrogen lines in that spectrum. And so that sounds probably a lot more complicated than it really is. So I'm going to kind of demonstrate what our calibration curve is, and again, kind of like just talk you through what the steps are that we'll really be doing. And so calibration curves, these are typically curves that are going to, really it's just a plot. You're going to be making a plot where you have measured known quantities. You're going to be measuring them in some very specific, consistent way, and you're measuring things that you already know, kind of like either a concentration of, or in this case, like our helium line spectrum, we're actually going to already know what all the wavelengths are for all of the lines in that spectrum. We're going to be given that information. And then we can make a calibration curve by doing some kind of measurement. In this case, we call it a scale reading that I'll show in kind of our next slide. But it's also applied to things like concentration. So if you have known concentrations, you can measure different values that are specific to the concentration or related to the concentration. And then from that, you can actually find an unknown value that's related to it. So like in the case of like 1212, we have a new lab that we've added now. It's called Beer's Law. In that case, you can measure basically kind of the intensity of color really in a solution and relate it to its concentration. And if you do that for a bunch of known concentrations, then you can actually find the concentration of an unknown solution. And so we can kind of do something similar here with wavelengths for these calibration curves that we're going to make. And so we're going to be using this process to find, as I said, unknown concentrations most of the time. In our lab, we're going to be using it to find the wavelengths of the hydrogen line spectrum. That's what we're going to be focusing on. So sample calibration curve. This is going to look like what you could see when you plot data, but you're basically going to be making a plot, and this is not what yours will exactly end up looking like, although it should be somewhat similar. It'll have more data points than what this one has, but you're going to be plotting wavelength along your x-axis, And probably for just good measure, I would probably make sure there's units on here as well. Right? If you're looking at these should say nanometers here for the wavelength. And then you have in this case, we have just what we call a scale reading. So this is some way of measuring where things are, and this can be done like really if you are able to kind of separate out these wavelengths. A lot of ways this is often done is like using a prism, kind of divides light out in a way that you can actually kind of measure things like how far the light's bending through something called refraction, and you can actually then measure your what's called the scale reading, oftentimes just like an actual length, like either millimeters or centimeters or something, and then you can make an actual kind of correlation between the scale reading that you have to the wavelength. And notice we have a best fit line here. We're able to make a linear fit to all of our data points. We have an equation for that line, pretty good R squared value, pretty close to 1. And that means that if we use this equation, the x in our equation is wavelength, y is our scale reading. Well, if we know the y value, the scale reading for our hydrogen lines, we can now solve for the x, which will be our wavelength. And that's effectively what we're going to do with the data that you have on CSE Pub. And so the calculations you'll be doing this week, you're going to make one of these calibration curves and use it to basically get a best fit line here with some equation. And then from scale readings for the hydrogen lines, you can use that to find the wavelength for the hydrogen lines. And then also then find the energy for those hydrogen lines and also the energy transitions that are happening for our electrons, like which energy levels are the electrons moving between to generate those particular wavelengths. So those are kind of the main calculation pieces that you're going to be working on this week. And I'm not going to detail too much more here because I think that's what you'll be talking about in lab. And so I'll let kind of your individual lab instructors go over that little bits in a little bit more detail. So hopefully that gives everyone kind of enough background information to get familiar with some of these things. I know calibration curves are probably something that are new, and I know not everyone has necessarily started the light chapter yet. So hopefully this is at least kind of a quick run through of a lot of the important things you'll need to know for this week's lab.